just coming here made me realize how much better an in-person conference still is. It doesn't even compare. So it's been really great being here again.
Hi everyone, my name is Julia. Thank you for joining my talk today. The title of this talk is An Editor Can Do That, Debugging Assembly Language and GPU Kernels in Visual Studio Code. And I'll definitely be showing both of these things today, but I also have another demo for you to show off some of the new VS Code GitHub integration and setting up efficient continuous integration pipelines for Raspberry Pi development specifically. So we have a lot of content, a lot of demos to get through. I'm really excited about it. I'd appreciate if we could hold questions until the end to make sure that we get through everything, but I'll definitely be around afterwards to answer all your questions. So welcome to day 4 of CppCon. We're almost through the week. It's pretty crazy. If you haven't already, please join the Visual Studio channel on Discord to chat with the Visual C++ team at Microsoft. You can ask us any questions there, discuss the latest announcements or anything that you heard in the sessions that you find interesting. And while I hope that you've all learned from us this week with our sessions, we also would love to learn from you. So please take our survey following that aka.ms link on the slide. It helps us build better products for you. I'll tell you a little bit about myself. So I'm a program manager on the Visual C++ team at Microsoft, and I've been on this team for about 1.5 years. I've been at Microsoft for 3 years, and before that, I was a computer science student at the University of Michigan. If anyone here has taken computer science at the University of Michigan, you might remember that the core curriculum classes are all taught in C++. So C++ was my introduction to programming, and I'm happy to be on a team with a mission of empowering C++ developers to achieve more. Okay, so can I get a show of hands for people who are currently using Visual Studio Code for C++ development? Okay, nice. We got quite a few people. So for those who are unfamiliar with VS Code, I'll give you a brief overview. According to this year's results for the Stack Overflow Developer Survey, VS Code is the #1 most used code editor. And it's easy to get started with because, first and foremost, it's free, it's cross-platform, and it's lightweight. I'm going to talk a little bit about lightweight. I feel like that word gets thrown around a lot. So when you install Visual Studio Code out of the box, bare bones, it has some language support built in, but in order to get that rich IntelliSense and debug experience, you need to install language-specific extensions, which means you're totally in control over what you're installing, and you know the support level that you need for different coding languages. And even when you install the C++ extension, for example, it's not installing a compiler or debugger for you. It uses whichever compiler or debugger you have on your system to set up IntelliSense for your project. So that means you can use the C++ extension with Clang, GCC, or with MSVC if you'd like. By cross-platform, I mean 2 things. The first is that Visual Studio Code and the C++ extension run natively on a ton of different platforms and architectures on those platforms. What I also mean is that you can easily target a platform different from your host operating system with Visual Studio Code using the rich remote development experiences. So you can install the remote development extension pack and then target a different platform either with WSL, with SSH, or with remote containers. And I'll be demoing the remote SSH extension a bit today. As far as C++ specific experiences go in VS Code, we're good. Our team at Microsoft maintains 3 extensions. The first is the C++ extension, which gives you IntelliSense and debugging for C++ files. And the second is the CMake Tools extension, which allows you to configure, build, and debug CMake projects in VS Code. And the third is the Makefile Tools extension, which is very similar in nature to the CMake Tools extension, except that it's for Makefile projects rather than CMake projects. So for those that are currently using VS Code, you might be thinking, I know all of this stuff. Please tell me something new. So let's get into the new stuff. The first thing that I want to talk about, and I'll be demoing today, is GitHub Codespaces. Can I get a show of hands for people who have heard of GitHub Codespaces, know what it is? Okay, a few people. So GitHub Codespaces is a cloud-based development environment for Visual Studio Code. You can think of it as VS Code backed by high-performance VMs that start in seconds, and you can access that cloud-based development environment from your web browser. So you essentially can code with Visual Studio Code in your web browser and get full C++ IntelliSense and build and debug support. So this means you can use VS Code with GitHub Codespaces on any device that runs a web browser, including like an iPad. And I had a coworker who tested it on his Tesla computer, so. And can I get a show of hands for people who are using CMake to build their C++ projects? Quite a lot of people. And now keep your hand up if you're using CMake presets. No one. So CMake presets are new. And one common problem that CMake users face is the ability to share common configure options with their teammates. Earlier this year, Kitware released support for a new file called CMakePresets.json, which lives at the root of your project. And in this file, you can specify all of your configure, build, and test options for CMake, and then check that into source control. And you can use that file to drive CMake from the command line, in a CI pipeline, in Visual Studio, and in Visual Studio Code, and any other editor or IDE that enables support for presets. So the CMake Tools extension in VS Code supports the latest version of CMakePresets.json, and I'll be demoing that today. Okay, can I now get a show of hands for people who are targeting, either developing on or for any ARM-based devices? Okay, I have good news for you. So last year at CppCon, we announced that the C++ extension runs natively on Linux, ARM, and ARM64, which gave you C++ IntelliSense if you were targeting a Raspberry Pi from your local VS Code desktop. At the time, VS Code did not have an official build for Linux ARM or Linux ARM64, so you didn't get the debug support. Since last CppCon, VS Code has released stable builds for Linux ARM, Linux ARM64, Windows ARM64, and Apple Silicon. So you can actually install VS Code directly on a Raspberry Pi and run it on the Pi if you prefer to do that. Another new experience in VS Code this year is for CUDA programming. So CUDA is a parallel programming platform that enables developers to interact directly with the GPU, achieving massive amounts of parallelism. And earlier this year, Microsoft and NVIDIA partnered together to light up the CUDA development experiences in Visual Studio Code. And that involves IntelliSense for CUDA files and CUDA code embedded within C files. And it enables you to actually debug GPU kernels. So I'll be demoing this for you today as well. Another new feature is disassembly view while debugging, and this was our top voted issue on GitHub for a long time. So we're really excited that it's now publicly available in VS Code. It's still in preview, and we have more features that we plan to add to it, and we'll continue to enhance it. But definitely check it out. Let us know what you think. I'll demo this today as well. And this, while it was a top ask for the C++ extension specifically, it's actually built into VS Code Core, so other extensions other than our C++ extension can enable support for disassembly view as well. Okay, the last new thing I'll mention for today is the Makefile Tools extension. So this extension lets you configure, build, and debug Makefile targets, and it reads from the Makefile in your project's directory. This is also in preview mode, and we have, if you go to the Makefile Tools GitHub repository, we have a document there with about 75 open source Makefile projects that we've tested the extension with. If your project is not on that list, please test out the extension. Let us know how it works for you. And yeah, your feedback is really valuable. So building and debugging CMake projects, disassembly view, GPU debugging, that's all pretty hardcore for a so-called editor, right? Well, I talked to a lot of people, and they just use Visual Studio Code for editing files, but you can do so much more with it, especially when you combine it with GitHub. So today I'm going to show you how when you combine VS Code and GitHub, you have everything you need for each step of your development workflow. And while I'll be using a Raspberry Pi in my first few demos, the experiences and their values hold true for all types of C++ development, whether you are doing GPU programming, programming on a Surface Pro X, or from the web browser on your iPad. So here we have the high-level lifecycle of a C++ application, or any application really, right? You write your code, you build and debug your project, you test your program in a continuous integration pipeline, and you maintain your program by making edits and committing those changes to version control, and the cycle repeats itself. So I want to talk a little bit more about testing your program in a continuous integration pipeline and how you can use GitHub code spaces and GitHub Actions to do that in a very efficient workflow. So what is continuous integration, also commonly referred to as CI? Continuous integration is the process of automating the build and testing of code every time a team member commits changes to version control. And it's really helpful because it reduces risk. You can easily detect and locate errors because you know exactly which commit is causing these checks to fail. It ensures quality because code won't be merged into a certain branch or released to production unless it's passed all of these automated tests. And it enables efficiency because you can spend more time coding and less time manually testing or waiting between test results and deployments. But you need a server to run your builds and tests. And what I've been using for my continuous integration workflow is GitHub Actions. So what is GitHub Actions? GitHub Actions offers workflows that build and test your code. And on the screenshot on the left, you can see what it looks like in your repository's UI. So you go to the Actions tab, and then you can see for each commit that you've made to that repository, the status of the checks that you've specified. So if it's orange, that means the check is in progress, it's running. If it's green, it succeeded. If it's red, it failed. So when do these checks run? Well, you can choose which GitHub events will trigger your workflows. So for my first demo, I've defined a workflow that will build and test my CMake project on a Raspberry Pi. And that workflow will be kicked off anytime I push changes to my repository. But you could edit that. You could also have the workflow kick off anytime you open a PR, et cetera. There are a bunch of GitHub events that are supported for workflows. So where are these workflows actually running? You have two options. So you could either run your workflows on a GitHub-hosted virtual machine or a self-hosted machine if you have a device that you want to be using to build and test your code. So in my demo, I turned my Raspberry Pi right here into a GitHub runner, and every time I push changes to my repository, this thing builds and tests my code. And yeah, so GitHub hosted or self-hosted. And how do you do this? So workflows are defined in YAML files in your project's .github/workflows folder. And it's really easy to create these YAML files because GitHub Actions will provide templates for you based on what it knows about your project. So for example, when I went to create a new workflow for my Blink C++ project, GitHub Actions presented me with templates that were specifically for building and testing C++ projects. So I picked the CMake-based project because I am using CMake to build my code. And then I edited the CMake YAML file to use CMake presets, which we'll get to in further detail later on. But you can actually do more with GitHub Actions than build your code and run unit tests. Oh, we're back, okay. You can use it to run code safety checks. And Sunny actually announced this in his talk on Tuesday. So there is now a Microsoft C++ code analysis GitHub action available. And this bottom screenshot shows what it'll look like in the UI if you submit a PR, and it'll run these code safety checks for you on your code base. And then you can see exactly in your PR what's triggering some alerts. But you can also see all of the code scanning alerts for the entire repository, not just what's been changed in your PR, as long as you're a branch owner. If you're interested in this, definitely check out Sunny's talk. The recording's online. He does a great job going into detail about it. Okay, so let's see this in action. No pun intended. For this first demo, I will be showing you how to set up a CI workflow for Raspberry Pi using GitHub Actions and GitHub Codespaces. Okay, cool. So here I have my Blink project repository open on GitHub. This is just a simple program that will blink an LED on my board from using my Raspberry Pi. And it's using a library called Wiring Pi, which actually comes pre-installed on Raspberry Pi 4. So I can see that there's a pull request open on this repository, and whoever did this PR is me, but you can imagine it would be like a teammate opening a PR on your shared repository, and that person wants to change the blink rate from 100 milliseconds to 1,000 milliseconds. And I think, no, that's way too slow. I don't want to change it to 1,000, but maybe like 500. Now, if I wanted to make that change, I could just do that right here in GitHub's PR UI, but with any change, even if it's a minor one, I prefer to make those changes in the editor because I want to have IntelliSense and make sure I'm not making any typos. If it's a larger project, you might want to do a find all references and make sure you understand exactly where the variable is being used if you're changing a variable's value. But switching from your browser to your editor, it disrupts your productivity because you have to make sure that your local version of the repository has all the latest changes, deal with any merge conflicts, and you're switching contexts. It's a lot of back and forth. So here's a neat trick that you may or may not know. If you have a PR open or the main page of a repository and you hit the dot or period key on your keyboard, then it'll open it in something called github.dev. So this is a serverless version of VS Code in the browser. It's different from GitHub Codespaces because it's serverless. And here I'm taken exactly to the context of the PR that I was just looking at. If you're on a device where hitting the dot or period key is not easy, you can also just change the .com in the URL to .dev and it'll do the same thing. So let's take a look at what this looks like in github.dev, and I can zoom in a little bit. Okay. So when you are in github.dev, one cool thing about it is that if you make any changes, they're committed directly to the branch. You don't have to do that extra step of pushing those changes. So here, I don't like that this is 1,000 milliseconds. I want to change that to 500. And then I can go to source control, see the changes, stage them, add a commit message. Commit, and those have been committed directly to my branch. And you can also switch branches easily or create new branches from this github.dev environment, and any unsaved changes on one branch will be saved. They'll remain on that branch. Now, because this is serverless, not all extensions work in github.dev. So the C++ extension, unfortunately, is not available here. Some extensions are, like the Python extension. You can totally use that here. But because the C++ extension isn't supported here, it's great for quick edits and like seeing all of the source files in your project. But if you want full C++ IntelliSense, so imagine this is a larger project and I wanted to do a find all references before committing these changes and merging the PR, then you need to use the C++ extension, and you have two options. So you can continue working on either a code space if you want to keep working in the browser, or you can clone the repository locally and open it in VS Code Desktop. So I want to keep working in the browser, so I'm going to say create new code space. And this would be really helpful because in this whole workflow that I'm showing you right now, you don't have to have anything installed on your machine. You don't have to clone the GitHub repository locally. You don't have to install Visual Studio Code. So if you're using someone else's computer that's not your own, or you're at a library or something and you don't want to install these things, GitHub.dev and GitHub Codespaces are an awesome way for you to be able to access your repository and make changes to it. Okay, so here I have my blank.cpp file. And so what a codespace is it's a Linux-based container that's the development environment for your project. And the default codespace, if you just say create new codespace, which is what I just did, we often refer to that as the kitchen sink because it comes with a bunch of tools installed. It comes with Python, Java, .NET, GCC, GDB, the C++ extension, the CMake Tools extension. It basically sets up an environment so that whatever kind of development you're doing, you have the tools to get started. But you can customize that configuration file if you have specific tools that you know you're going to want to be using that aren't in this default configuration. And then you can share those configuration files with teammates so that and check those into source control so that you all have the same clean, consistent development container for your code space. Now, you've probably noticed that there's a red squiggle line here. Can anyone tell me why that would be? Exactly. So what I said is that the Wiring Pi library comes pre-installed on a Raspberry Pi. And this default code space that was created for me is not a Raspberry Pi. You have a few options if you wanted to do Raspberry Pi development with a code space. You could customize the configuration to use a Raspberry Pi Docker image. You could set up port forwarding from your code space to your Pi. Or what I'm going to do today is set up a continuous integration pipeline so that whenever I push changes to this repository, they'll be built and tested on the Raspberry Pi. So in order to kick off that workflow, I'll need to make a change and push those changes. But actually, before I do that, let me just show you how you have C++ IntelliSense in a code space. So you have things like quick info if you hover over variables. You have autocomplete. And you could do find all references here. This is all in the browser. And you can even build and debug in a code space, either through this build and debug pane and creating build tasks and launch configurations, or if you have a CMake project, you can build and debug using CMake Tools in your code space, which is where these icons in the blue status bar at the bottom, those are coming from the CMake Tools extension for configuring and building your project. So let me make my change. I'll just add a comment here for num blanks. And then if we go to the source control, we will commit and push these changes the same way that we did in github.dev, except we'll have an extra step of actually pushing the changes. Okay. So now you can look at your pull requests also in GitHub Codespaces and in VS Code Desktop and in github.dev. So you have this cool pull request UI where you can see all of the commits that were made and the files that were changed. And you can see it says right here, one pending check. So that's the build and test check that I've configured for this project. And let's look at that in the browser to see that in more detail. Okay, and it looks like in that time that I opened the browser, the check succeeded here, which we can see with that green check mark. So let's take a look at what this is doing. So it's setting up a job, and it's using my Raspberry Pi, which I set up as a self-hosted runner. And it's really easy to do that. You just run a few commands in the terminal, and it's all in GitHub Actions documentation. But if you are using a self-hosted runner, it's recommended that you only do this for a private repository. And you can add self-hosted runners at the repository level, at the organization level, or at the enterprise level. So this is really helpful if your team has 1 or 2 Raspberry Pis, not enough for everyone. You can just set those up as GitHub runners, and then whenever anyone on the team pushes changes to the repository, the workflows will be kicked off on those Pis. So the configure and debug on Raspberry Pi. So this is running, this is using CMake presets to configure and build the project. And then same thing for CTest, it's using the test preset that I defined, and you can see the tests are passing. So let me show you what this actually looks like in the YAML file. If I go to my code, and then in my workflows folder, I have the CMake.yaml file. Let me zoom in a little bit. Okay. So a workflow is made up of one or more jobs. And so here's my build job, which actually is a build and test job. And for each job, there's this runs on property. So that's where you specify if you want it to be run on a self-hosted device or on a GitHub virtual machine. Another thing that you could do if you wanted to use a GitHub hosted runner, but you didn't want to use Windows, Ubuntu, or Mac OS, because those are the available VMs that they have, you could also run these jobs inside of a Docker container on the GitHub hosted VM. So that's another way to get around running it on a platform that's not available as a GitHub runner. And then here for the configure and build on Raspberry Pi, I'm using presets. So what I have in this CMake.yaml file, like these 2 lines, this is exactly how you would how you would use CMake presets from the terminal or on the command line. It's just copy and pasted. And same thing with running CTest. So I now want to dive into CMake presets and why they make it very easy to invoke consistent CMake builds from the command line in a CI pipeline in VS Code. But first, let's exit the demo, get back to the slides, and we can talk about what presets actually are. So I've put slides for each of the demos that I'm doing with the extension IDs for the extensions that I used in the demos so that you can install the same ones. So for the demo I just did, I actually didn't manually install anything. When the default code space was spun up for me, it installed the C++ extension and the GitHub pull requests and issues extension for me. I did not use the GitHub Codespaces extension today, but that is something you could use with VS Code Desktop if you wanted to connect to your code space, but still use, your local desktop version of VS Code. Some key takeaways from that first demo is that github.dev and GitHub Codespaces enable you to write and commit code directly from your web browser on any device, which is great because you don't need to install an editor or clone a repository on the machine. GitHub Actions makes it easy to build and test your code in continuous integration, continuous deployment workflows. And you can use a GitHub hosted runner or a self-hosted runner for more control over the hardware and OS. Okay, so let's talk about CMake presets. So one common problem that CMake users face is not being able to share their configure options with teammates and not being able to replicate consistent builds in different environments, whether it's in an editor or an IDE or from the command line. So earlier this year, Kitware released support for this new file, CMake presets.json, and it requires CMake 3.19 or later. The latest version of this file, which is v3, which is what I'm using in my demo today, requires CMake 3.21 or higher. And what the latest version of this file has is not just configure presets, but also support for build and test presets. So any options that you normally would pass to CMake on the command line when you're configuring, building, or testing your project, you can specify all of those in this JSON file, put that in your project root directory, check that into source, and then Visual Studio and Visual Studio Code can read from that file to configure, build, and debug your program. Or you can use CMake -- preset and specify the presets you want to use on the command line to invoke the same builds on the command line. So that file is intended to be checked into source control, but it has a companion file called CMake user presets.json, which is intended for developers to save their own local builds, and that does not get checked into source control. So I'm using CMake presets for my blank project, and I have 2 configure presets that I've set up. One is for debug, and one is for release. So here's an example of the debug preset that I used in my CI pipeline that you just saw. So each preset has a unique name. So raspi-debug, that's what you would use if you were invoking this from the command line. That's what you would pass to CMake with the -- preset flag. It also has a friendly display name. That's what you would see in the CMake Tools UI in Visual Studio Code. And if you look at this example configure preset, all it's doing is setting the CMake build type cache variable to debug. It seems a little bare. So it's also inheriting something called base. So CMake presets support inheritance, and it's common practice that you would have a hidden base configure preset that sets things like the architecture and the generator, the install directory, the binary directory. And then you can define additional presets that inherit from this base configure preset and either add additional properties or override some of the values in the base configuration. So this is the base configure preset that I have for my Blink project. Most of these options correspond to, or most of these properties correspond to options you would pass to CMake on the command line. In fact, any option that you can pass to CMake on the command line is captured by configure, build, and test presets. So for example, setting the generator is the same as passing -G, setting these cache variables is the same as passing -D on the command line, and the cache variables and environment variables are inherited by any preset that is inheriting this base configuration. This is an example build preset. So this is a verbose build. It passes -V to Ninja. And a single build preset corresponds to a single -- build invocation to CMake on the command line. But you can define as many build presets as you'd like in your CMake presets JSON file for your project. And you can see here I specified a configure preset for this build preset. So there's a one-to-many mapping for configure preset to build preset. And the build directory is inferred from whatever the configure preset is that you specified for that build preset. Okay, so let me show you now how to use CMake presets and Visual Studio Code to run and debug a program on a Raspberry Pi. Because what I did in the first demo, enabling automatic building and testing in a CI pipeline, that's obviously great and is amazing for catching bugs and ensuring high quality products, but it obviously doesn't replace running the program and debugging it on the Pi. So I'll show you how to do that with CMake Tools right now. Okay, so I'm going to be using the remote SSH extension to SSH into my Pi from VS Code, which is running on my Windows laptop. I recommend installing the remote development extension pack because then you get the remote WSL extension, the remote containers extension, and the remote SSH extension. And once you have these remote extensions installed, you'll see this remote explorer icon here on the left. So this is a list of all of the SSH targets that I have previously connected to. And if you wanted to add a new one, you just click this plus sign and add it there. So I'm going to connect to this last one in the list because that is where my project is. Actually, you know what? I think it's this one. And you can go directly into a folder if you've already opened that folder on the remote target before. Okay, it was not that one. Let's see. Okay, there we go. So if I look at the extensions in the extensions view, I can see which ones I have installed locally on my Windows laptop and which I have installed on the remote target. And if there are extensions that you have installed locally that you want to install on the remote target, you can just click this cloud icon and then select the extensions that you want to install over there. Little shortcut. Okay, let's look at CMake presets.json. So one thing to notice is that the CMake Tools extension provides IntelliSense for this file. So you can hover over properties to see helpful descriptions about what they are. and you'll have autocomplete. And if we look in this CMake presets JSON file, we can see here I have my hidden base configure preset. I have my debug preset, and I have my release preset for configure. So when I go to select a configure preset using the CMake Tools UI, I should not see the base one as an option. That's hidden. I should just see debug and release. And you can select your configure preset by hitting this button in the blue status bar. And yeah, I see my two options here. So I'll select debug. And then to configure the project, we'll open the command palette and type CMake, and then we'll select delete cache and reconfigure. So I want to call out that all of the commands that are available in the status bar from the CMake Tools extension, you can also access from the command palette by typing CMake, and then you'll see all of the commands provided by the CMake Tools extension. Okay, so the configuring was successful. We now have our build files. So I'll select my build's target as verbose build and hit this build gear in the status bar. And we've successfully built our program. Okay, so now let's actually see this LED blink, and you can see the program run live. And I will basically start a debug session and then change the value of this delay time variable during that debug session so we can play around with different blinking speeds. And I will also open disassembly view so you can see what that experience looks like. Okay, so I'm going to set a breakpoint in my for loop, but I'm going to add a condition to it because I want to actually see this thing blink a few times so I can see how fast the speed is and then change it. So let's break when I is 8. Okay, and now we can hit this debug icon here. And it's worth noting that the CMake Tools extension just read from my CMake presets.json file. I didn't have to do any additional configuring or create any other JSON files or edit any of the extension settings. It just worked. Okay, oh, I need to switch to this camera so you can see it blink. That's the wrong camera, sorry. That's also wrong. Okay, there we go. Let me run this again so you can see it. Okay. So we should only break once this has blinked 8 times. And it's blinking. And for some reason, when it's lit up, it just disappears on the camera. Okay, so now let me go back to VS Code. And once we hit our breakpoint, then we'll be able to see all of the local variables and play around with those. So I'm going to change this delay time by using the set value option. And let's speed that up. Let's make it 500. And then we can resume our program, go back here, and you can see now it's blinking twice as fast. Okay, but sometimes you want to debug more than just the source code. You want to actually look at the assembly language created by your compiler. So you can now do that in VS Code, and I will remove this condition because I just want to break on this the first time we hit it. So to open disassembly view, you start a debug session, and then right-click on your source code and select Open Disassembly View. And here we have the memory address for the instructions and the machine language displayed as hex and then as assembly language in the right column. And so one feature that we are working on, and it is just about ready, is being able to see the source code in line with disassembly view. What you can do for right now is split the screen, and then you can look at your source code side by side with disassembly view. And you can step through disassembly just as you would with your source code, and you can set breakpoints in disassembly view and disable them the same way that you would with your source code. One other thing I'm going to show you with the CMake Tools extension and CMake presets is the ability to run tests with the CMake Tools extension. So in my CMake presets JSON file, I have one test preset, and that I have selected down here in the status bar. And I can already see right here it says 2 out of 2 tests are passing, but you can click on that again and it'll run the tests and you can see the output. Okay, we'll go back to the slides. So the extensions that I used in this demo are the CMake Tools extension, the Remote Development Extension Pack, and the C++ extension. Some key takeaways from this demo is that VS Code provides full C++ IntelliSense and debug support for Raspberry Pis, and you can use disassembly view to debug assembly language. You can develop on and for a Raspberry Pi with VS Code by either installing VS Code on the Raspberry Pi and connecting your Pi to a display and running it there, or installing VS Code on your laptop and using the remote SSH extension, which is what I did. Another key takeaway is that CMake presets.json enables consistent builds from the command line in CI/CD pipelines from Visual Studio and VS Code. I had that same file. I had that file in my checked into source code, and that was used in my CI pipeline and used in VS Code. So at this point, you've seen that whether you are making changes in the web browser and committing those changes directly to the repository without needing to switch context, or if you are debugging with disassembly view on VS Code Desktop on a Raspberry Pi, or you're kicking off builds and tests in a CI pipeline using GitHub Actions, you've seen that VS Code and GitHub work very nicely together to help you out at all stages of your development workflow. And while I used a Raspberry Pi and a simple embedded project in these demos, the experiences and their values are true for a variety of C++ application types. And speaking of different types of C++ applications, I'm going to switch gears and show you how to build and debug CUDA programs for those of you who are doing GPU programming with Visual Studio Code using the Nsight Visual Studio Code Edition extension, which NVIDIA built. So, quick reminder of what CUDA is. CUDA is a parallel programming platform that enables you to interact directly with the GPU, achieving massive amounts of parallelism in your program. And you can use the C++ extension to get CUDA IntelliSense and the Nsight Visual Studio Code Edition extension for build and debug support for CUDA programs. So I am using the remote SSH extension here because I actually spun up a virtual machine in Azure that has a CUDA-capable GPU. So the remote SSH extension is also really helpful for CUDA programming in VS Code, in my opinion, because if your local machine doesn't have a CUDA-capable GPU, or you just prefer to have a cloud-based development environment in general, you can still target that machine from Visual Studio Code and get the full CUDA IntelliSense and GPU debug support. So I've spun up this VM in Azure, which I can actually show you right here, Azure NC series. And for the sake of time, I've already connected to this VM the same way I connected to my Pi using the remote SSH extension. And the sample project that I'll be using in this demo is the Matrix Mole project that comes as a sample project with the NVIDIA CUDA toolkit. So let me just show you, let's double check we have a CUDA-capable GPU and that we have CUDA GDB and NVCC, which is for compiling your CUDA programs. So I have the CUDA 11.4 toolkit installed on this VM. Okay, so right off the bat, you can see that semantic colorization and syntax highlighting is working as it should. If we have things like find all references. So here I'm doing a final references on this matrix mul CUDA kernel. And then we have autocomplete and signature help and quick info, which is just helpful information that shows up when you hover over a variable or type. So essentially what I'm showing you is that the IntelliSense that we have for CUDA is on par with the IntelliSense that you can expect for standard C++ and C files. Okay, so now let's build and debug this project. So if you use the sample project that comes with the NVIDIA CUDA toolkit, they'll actually provide this .vs code folder with the JSON files. So your build tasks live in this tasks.json file. And we can see this build task is using make. And if we look at all of our files, you can see we don't currently have an executable or object files. I ran a make clean before this demo. And this property right here is default is true, means that we've hooked up this build task specifically to the Control-Shift-B keyboard shortcut. So if you had multiple build tasks, you can mark one of them as default, but you can still call the other ones. So let's build this project. So I'll use Control-Shift-B. And another way you could do that is go terminal and then select run builds task. And the executable and the object file now appear here in the File Explorer. So we had a successful build. Let's say you had a compilation error in this file. So if I added a space here, then all of those problems show up here in the problem matcher, and you can click on them to be taken directly to where the issues are. So let's remove that, save the changes, and the problems go away. Okay, now let's get to the GPU debugging portion of this demo. So I'm going to set 2 breakpoints. I'll set one at the start of the main function, and I'm using this outline feature to navigate to different parts of this file. And we'll also set one in our CUDA kernel. So that way we're debugging both the CPU and GPU portions of this program. So our debug configurations, similar to how build tasks live in task.json, debug configurations live in launch.json, which is also in your projects.vs code folder. So this debug configuration is using CUDA GDB that I have installed on the VM to debug this program. And if you wanted to create a new configuration for CUDA, you could just click this Add Configuration button and then select C++ launch, and then edit the program name and add any additional debug properties. So that selection, that option to select CUDA C++, that's provided from NVIDIA's Nsight Visual Studio Code Edition extension. Okay, so we have our debug configuration all set up. Let's start debugging. So you can either select Start Debugging from the Run menu or just hit F5. And we've hit our first breakpoint, and we have CPU registers here. We're just at the start of the main function. When we continue our program, we should stop only once we've hit our GPU kernel. So we're now in our kernel, and if we take a look at the registers, we actually have GPU registers now. And all of the local variables, this is all reflective of the GPU portion of our program. So recall that CUDA is a highly parallel programming platform. So when a CUDA program is executed, it's executed over hundreds or thousands of threads in parallel. And those threads are organized into things called blocks, and then blocks make up what's called a grid. So you have a lot going on at once, but you can actually index into a specific block or into a specific thread to debug specific portions of the GPU. That's called the focus. So you can change the focus in Visual Studio Code once you are debugging the GPU by clicking on these indices in the bottom right of the status bar. And I'm going to set my block X index to 1. And for thread, we'll do 5 to 0 for the XY is 5 and 2. So I hit enter, and now if I go to the debug console, you can see the output from CUDA GDB that says it's switching the focus to the block and thread indices that I specified. And we can see that the value of our local variables for the X thread index and X block and Y thread index, those all changed to what I specified when I was changing the focus. Oh, one other thing that I'll show you for debugging CUDA programs in Visual Studio Code is that if you are used to using CUDA GDB in the terminal, you can interact with CUDA GDB in the debug console the same way that you're used to. Just put a backtick before any of the commands. So if you do backtick and then write info CUDA kernels, you'll see the output from CUDA GDB the same way you would when you do this separately in the terminal. Okay, so the extensions that I used in this final demo are NVIDIA's Nsight Visual Studio Code Edition extension. I used the remote SSH extension within the remote development extension pack to target my Azure VM with my CUDA-capable GPU. And I used the C++ extension, also called CppCon Tools, not to be confused with CMake Tools. I used this for my CUDA IntelliSense. Some key takeaways from this final demo is that the C++ extension provides IntelliSense for CUDA C++ programs, and the Nsight Visual Studio Code Edition extension provides build and debug support for CUDA programs, including GPU debugging, where you can do things like change the focus. And you can target a machine with a CUDA-capable GPU using the remote SSH extension. Okay, I showed you a lot of demos and new information today, but we also have some other new things in VS Code that I'll touch on briefly. So the first is the Makefile Tools extension. I already talked about this, so I won't spend much more time here. And then we have a few things that are coming soon. So the first is Clang Tidy integration, so you'll be able to see the results of Clang Tidy checks in your editor. And the second one is the ability to create definitions from declarations and vice versa. This has also been one of our Clang Tidy, and the ability to create definitions from declarations have been some of our top asks on GitHub for a while, so we're excited to be working on those. For those who are unfamiliar, we turn to our GitHub repository and the issues on our GitHub repository to kind of figure out what we should be working on. So if you use the C++ extension and you have an idea for a new feature, you run into a bug, definitely open an issue on our GitHub repo or upvote an existing issue to show that you care about it and you want it. Here's a link with some helpful resources. I will make sure that these links are either clickable in whatever version of the slides I upload online after this, or I'll change the links to be the full URL so you can copy and paste. One thing I'll mention is the C++ extension pack, which includes a lot of the extensions I showed you today, including the C++ extension, the CMake Tools extension, the remote development extension pack, and some more. Some other third-party extensions, including one that provides IntelliSense for CMake files. So I would recommend installing the extension pack to kind of get you all the extensions you need to get started with your C++ development workflow. Thank you so much for listening to this talk. I hope you enjoy the rest of the conference. Please, as I said before, if you want to talk to the team, please join our Visual Studio channel on the CppCon Discord. We no longer have a booth. That ended after Tuesday. And also, please take our survey if you have time. We have had a ton of sessions at CppCon this year. For the ones that already happened, if you missed them, feel free to check them out online. And we have 2 others after this. So Charlie's giving a talk on STD format, and Gabby's giving a talk about finding bugs using path-sensitive static analysis. Thank you so much. I think we have time for questions. Yes. I honestly don't know the extent of the list of the different ARM. Oh, sorry. Let me repeat the question. So the question was, I mentioned that VS Code has released builds for ARM and ARM64 architectures. And the question was, does it run on a variety of different platforms with ARM and ARM64 architectures or just Raspberry Pi? The answer is, I believe it's a variety. And you can actually, if you go to the Visual Studio Code download site, it'll list all of the architectures and platforms that it supports. I don't have an exhaustive list off the top of my head, though. I'm sorry. Second question. Good question. So the question was, if Visual Studio Code supports ARM and ARM64, does that mean the extensions also support ARM and ARM64, or do you have to wait for the extensions to enable that support? And it is the latter. Typically, the extensions will have to do some extra work to enable support for other platforms. Mm-hmm. Yes? Raspberry Pi OS. Yeah. Yeah, I think it does. I can actually, here, let me pull up. Okay, so I guess for Debian, Ubuntu, Red Hat, Fedora, SUSE based Linux distributions, it should work for ARM and ARM64. So you can. You don't have to. So in the demo that I ran today, I did not. The question was, does VS Code have to be installed on the Raspberry Pi? You can do that. And that was something that customers were asking for, so we enabled support for that. But you can also install VS Code on your personal laptop. And then because the extensions have enabled support also for Linux ARM and Linux ARM64, then you can target those devices using the remote SSH extension and any language extensions that have enabled support for that. Yes?
That NVIDIA demo, when you did the backtick and entered the GDB command.
Yeah.
Will that work with any GDB server? Because I used it to connect to like or whatever. Or is that specific to NVIDIA?
So the question was, in the last demo, when I entered a CUDA GDB command using a backtick into the debug console, does that work for just CUDA GDB or other GDB servers? I think it works for regular GDB. I think you can do the same thing, but I don't want to say that for sure if I'm wrong, but I will figure that out. And let me go back to the slides. Feel free to follow me on Twitter and I'll follow up on some of these things and tweet the responses to those. Any other questions? No? Yes? Sorry, can you speak up a bit? How is it profiling the CUDA code? Oh, is it possible to profile the CUDA code? That would be a question for NVIDIA. So the experience that I demoed for you today is using NVIDIA's Nsight Visual Studio Code Edition extension. So I would follow up with them or check out the documentation for that extension specifically to see everything that you can do with it. What I've worked with them on, and we've done demos in the past on, is exactly what I showed you today, the debugging, but I don't know the extent of everything that you can do with that extension, and I'm sure there's more. We have a question from online.
Does the CMake presets.json make obsolete the CMake kits feature from the CMake Tools VS Code extension?
Sorry, does CMake presets what was the second part of that?
CMake presets.json make obsolete the CMake Kits feature from the CMake Tools VS Code extension.
Oh, yes. So the question was about having CMake presets.json and how that works with CMake Kits, which is what the CMake Tools extension before CMake presets, that's what it used to build and debug your program. So if the CMake Tools extension detects a CMake presets.json file in your project directory, it'll automatically use CMake presets, and you should not even see kits or variants in the UI. You can change that behavior. There's a setting for it. So you can either choose to ignore presets or always use presets or have the default behavior. Okay, and the session is over. I'm getting the signal. Thank you so much.